Okay, the next speaker is Guochao Jasonson, who will talk about the unsettled use of galaxies, the physics and implications of Bursty star formation in the HiPACC universe. Thank you. The floor is yours.
Okay. So hello everyone. My name is Guochao Jasonson, a postdoc based at Northwestern University. So today it's my pleasure to share with you some recent work I've done with my collaborators on understanding the unsettled use of galaxies with a particular focus on the Bursty star formation history of high-Z galaxies from the fire simulations. So I guess we've heard about this overabundance problem multiple times, many times enough for me to not explain it again. But I just wanted to say that this is basically what motivates us to look into the business of Bursty star formation at cosmic dawn as a possible explanation. So from Claude Andre's talk yesterday, you may still remember this general picture of galactic phase transitions emerged from the fire simulations. So just to briefly recap, the star formation history plot on the left is showing you that the Bursty to steady star formation transition happens when galaxies grow massive enough. And the two snapshot on the right shows you the transition of star formation mode also coincide with phase transitions of the central galaxy, namely the disk formation process, and also the virialization of the circumgalactic medium. And so as I'll talk about later, this relates to an important distinction in the way that we can understand and describe high redshift galaxy formation. So to understand the explicit or exact implications of Bursty star formation for the observed galaxies at cosmic dawn, especially their abundance, we turn to a suite of high redshift Fire 2 simulations that were introduced well before the launch of JWST. And these high resolution simulations are able to explicitly resolve the effect of star formation and multi-channel stellar feedback in the interstellar medium. And in particular, they naturally predict the star formation in high redshift galaxies to be spatially clustered and temporally bursty. And here I should also emphasize that these simulations assume standard cosmology, and they predict normal galaxy scale integrated star formation efficiency. So by looking at the red frame UV brightness of the galaxies in our simulations, the first thing to realize is that Bursty star formation can strongly modulate the observability of galaxies. And the upshot is that galaxies flicker as their star formation rate fluctuates. And for galaxies near the detection limit of a given flux-limited survey, this kind of like flickering can cause galaxies to oscillate in and out of the observable regime. And for example, from the plot shown here, for an example galaxy Z5M11D from our simulations, we can see that how the galaxies jump into the observable regime due to a major starburst occurs around redshift 7.5, and then as the SFR drops, the galaxies just like phase away and becomes undetectable by redshift of Z of like 6.5. And you're welcome to check our paper to see how this kind of modulations of galaxy observability can induce selection effect for galaxy properties that are sensitive to burstiness. So for the abundance of galaxies, here on the left, the top panel shows you the relationship between the UV magnitude and the halo mass, whereas the bottom panel shows the corresponding UV luminosity function. And to calculate the UV luminosity function from our zoom-in simulations, we essentially or basically took the full distribution between the UV magnitude and the halo mass and perform a convolution with the halo mass function. And to gauge specifically the impact of burstiness on the observed galaxy abundance and to characterize the effect of Bursty star formation, we define two contrasting scenarios in which we evaluate the UV magnitude of galaxies differently. So as illustrated by the cartoon on the right, in the first scenario, which we call Bursty, the UV magnitude is evaluated from the SEDs of the star particles without any modification, so directly from the simulation. Whereas in the second scenario, which we call Smooth, we smooth the star formation history on purpose by redistributing the stellar ages or star formation times in order to average out star formation rate fluctuations over some given time scale. And this method is guaranteed to reduce back to the Bursty limit if we choose a short enough smoothing time scale. So from these comparisons, we found basically two main things. The first, our simulations without any fine-tuning can well reproduce the observed UV luminosity function all the way up to redshift 12, where we stop our analysis because of the limited sample size. And this includes a comparison with both the photo-Z candidates at some kind of upper limit, as well as the SPECT sample as conservative lower bound. And second, Bursty star formation appears to play a very important role in shaping the bright end of the UV luminosity function, especially at redshift above 10, where we can see that there's a order of magnitude difference in the galaxy abundance between the Bursty and the smooth cases. So one thing you might wonder about the discussion of burstiness so far is what kind of integrated galaxy scale star formation efficiency do these simulations predict? So here I'm showing you the stellar mass to halo mass ratio at the same redshift of the UV luminosity functions that I just showed. And we can see that despite an increasing scatter towards lower masses, the galaxy scale star formation efficiency remains at a relatively low level. And it basically barely differs from that at lower redshift in terms of both the slope and the normalization. And also, I want to mention that this agrees with the results from cosmological volume simulations that Robert talked about earlier this morning, which also use the standard fire 2 physics. So now we've seen the implications or the importance of Bursty star formation for understanding the observed galaxy number statistics at cosmic dawn. You might wonder, what other aspects of galaxy evolution Bursty star formation may affect. So, which at the same time inform us about possible ways to probe the physics of burstiness. So here is a quick example. I'm showing you some predictions about galaxy chemical evolution from an analytic model of Bursty star formation at cosmic dawn based on a delayed injection of supernova feedback. So from left to right, the three panels shows you for example, halo shows the halo's star formation history and the relationship between the halo's gas phase metallicity with stellar mass or the star formation rate. And basically, we can see that Bursty star formation in the low mass galaxies sources strong fluctuations in the gas phase metallicity and causes a large scatter at the low mass end of the MZR. So this kind of loosened MZR could potentially be used as a probe for the physics of Bursty star formation. And I also want to mention that we actually find something similar from our prior simulations too, and Andy in the audience will tell you more about that on Friday. So in the last couple of minutes, I'd like to discuss some ideas to theoretically understand and describe the high-Z star formation that is motivated by our simulations. So a key prediction of the FIRE simulations, as Claude Andre mentioned yesterday, is that the interstellar medium was dynamic. For those Bursty galaxies, the interstellar medium is dynamic and morphologically very disturbed without a clear boundary with the circumscribed galactic medium. So as shown by this plot, for a typical 10 to the 11 solar mass halo at redshift 5 and 6, the multi-phase gas in the halo has it demonstrated large fluctuations in terms of the density and temperature. And due to the strong stellar feedback, the gas doesn't form a stable or rotationally supported disk, as is often assumed in models of galaxy formation even at high redshift. So the ongoing star formation, here color-coded by the green contours, is pretty much restricted to only the cold and dense gas and spatially extends to large halo radii. So together, like these features, like kind of like provide the motivation for us to approximate the halo gas as kind of a density field of the turbulent flows, and in a way that is analogy to a turbulent molecular star formation in turbulent molecular cloud, but here applied out to the halo scale. So to see how the multi-phase gas may be approximated by the turbulent density field, we check and plot the probability distribution of the gas density contrast at different halo radii. And from the two plots here, you can see that the distribution of the gas at different temperatures are characterized by different PDFs, with cooler gas having higher densities. But the total distribution is still very well approximated by a log normal distribution. And the fact that the total distribution of the density contrast PDF is roughly log normal over the entire halo range means that, like, in order to model the gaseous halo with as some kind of like density field of turbulent flows, we can pretty much combine a simple parameterization of the density PDF with a radial gradient of the mean density of the gas, which largely follows the halo profile. So now if I color code the total gas density distribution or density contrast distribution with the mass fraction of gas that's actually forming stars, namely the mass fraction of gas particles with a non-zero SFR, we can see that there's a clear borderline between star-forming gas and non-star-forming gas, and the borderline sort of like moves to a larger radius because of the radial gradient of the mean density. But the most important feature here is that the star-forming gas is pretty much constrained to only the cold and dense gas in the very dense end of this distribution. And also you can see that this kind of borderline agrees with the kind of like star-forming criteria that fire uses to determine what fraction of gas actually forms stars. And finally, we can put the star formation in the context of this like turbulent framework to understand the normal, the kind of like normal integrated galaxy star formation efficiency predicted by our simulations. So here the three panels show you the radial profiles of the mean gas density, the mass fraction of mass fraction of star-forming gas, and also the radial profile of the star formation rate. And so you can see the good agreement between the simulations shown by the dots and the simple analytic picture shown by the equation here, or the solid curve in these panels, basically shows that the normal star formation efficiency can be understood by the fact that even though the star formation efficiency per free fall time can be as high as 100% as assumed in fire, if we because of the large density distribution induced by the turbulent flows, the star-forming gas actually only constitute a small fraction of the total mass of the star form of the gaseous halo, and therefore the resulting star formation efficiency on galaxy scale is relatively small. So I think in the interest of time, I'll just very quickly leave my summary slide here and take your questions. Thank you.
Thank you. One question, and the next speaker can start to participate.
I'm just curious, the dense clumps of gas that have formed, where these filaments have come in, like what sorts of relative velocities do they have? You mentioned that they're not in a rotating disk, but does the velocity dispersion among those clumps, kind of reflect a virial equilibrium, or have they not settled down that much?
I think from the energetics of the or velocity of those gaseous structures, I don't think they're in a very good virial equilibrium yet. So if you look at the total kind of kinetic energy, a lot of the system are still unbound. We haven't like explicitly checked the like exact comparison here, but my gut feeling is that like the kind of velocity dispersion compared to the kind of bulk velocity of the inflows, I think relatively it can be like a pretty large dispersion.
Okay, we need to move on, but we can go on with the questions maybe in the lunch break.